with section 11.3. So in this one, we're going to be talking about vectors. Okay. Normally in class, I would show you the little scene from Despicable Me, where you meet the villain Vector for the first time, and he's like, "Oh yeah." And he talks about what a vector is. He actually gives the very mathematical definition of a vector is that it is he's committing crimes with direction and magnitude. So that's what a vector is. It has direction. It has magnitude. A vector looks like a ray. So what you're seeing here, I've also provided you notes about vectors with all the information that you need as far as properties and the unit vectors and operations and things like that. So this section's pretty straightforward. There's not a lot of trig in here, but just a lot of information on how vectors work and some basic operations with them. Okay, so let's go ahead and get started. So here again, this is a vector. We call it, you can call this vector A, and generally what you would do is there's a lowercase letter associated with it. So we would put that lowercase letter right there beside it. When we write vectors, so vector A in here would be written, and they look like the greater than and less than symbols. And it'd be, well, horrible. I have A, but inside here, this would be component A and component B. Okay. They kind of look like, excuse me, they look like points. But again, instead of parentheses, you have these greater than kind of less than symbols that you're using here. And because they kind of look like points, they kind of act like points too a little bit. This is kind of like, think about it like as your X value, your Y value. And when you name a vector, you usually name it for the position vector, which is where its terminal point is, where the end of my arrow would have like a dot on a coordinate plane. Okay, that's called the terminal point, and this is what we call the position vector. Okay, that's how we kind of name it. Magnitudes of vectors kind of looks like absolute value, but it means magnitude. So let me put A in here. So this A right here is not the same A as what's over there. Please note, this is the name of the vector. This is the component like an X value. Okay, so magnitude, it looks like absolute value. You take the square root of A squared plus B squared. And again, and it looks like basically like the circle formula. Or sorry, not circle formula, but Pythagorean theorem, because what you're doing is the magnitude is like the distance of your vector. The distance of your vector. Okay. So those are some main pieces. We can talk about the angle of a vector because we can find that if we know the name of the vector, the position vector. You can use tangent theta is equal to B over A, which notice that the B is the Y value, kind of like the Y value, the A is like the X value. And that makes sense because tangent is Y over X. Okay. So there's how we can find, some different pieces. We can talk about the opposite vector, and it is opposite vector. We don't say negative vector, but the opposite vector. And an opposite vector looks like a negative A, but it means opposite. And this is what the opposite vector of this guy would look like. You basically start at the initial point where my vectors are first starting, and it goes, if I can kind of get it there. There we go. And opposite vectors, they start at that initial point right there, and they shoot off in the opposite direction. They go the same magnitude. They just have a different terminal point because they are going the opposite direction. Okay, so that's an opposite vector. This is what a negative A would look like. All right, let's make that turn colors for me. So that's an opposite vector. It goes in opposite directions. Reason why I have to say this, because for your first couple examples in your assignment, so question number 1, it gives you a picture of a vector like what I've given you here, and then it says which picture below shows the opposite of the vector. So again, it's going to start at that same initial point, and it's going to go the opposite direction. Okay, almost kind of like it's making a full straight line. All right. And then after that, they're going to start asking you questions about how do we add and subtract vectors. Okay, how do we add and how do we subtract? And they're going to give you a couple pictures to look at. So let me talk to you about adding and subtracting. So there are 2 ways to add vectors. When you are dealing with the vectors, oh no, nope, they're not connected. Let's connect those together so I can move them kind of as one. Okay? So when you add vectors, you can do it one of 2 ways. You can start at the initial vector, which is Q, and go that vector, and then all you're going to do if you want to add is pick up right where it left off and continue along vector V. Okay? And this distance that you see right in here, from here to here, actually, let me change the color. Let me actually do a line. So starting right here, all the way to the end of my vector V right there, that red line, that is your Q plus V. Oops, no capitals. So that red line right there represents the Q plus V. Okay? Let's change that up. Let's make it red. There we go. So that's one way to think about adding vectors. Okay? Another way, let me grab all this information. Let's clone it. We'll move it right down here. Is they think about it like a parallelogram. Okay? So let me grab this, move it out of the way. We'll move that up there. And what they do is they have both vectors starting at that same initial point. Okay? So we got both vectors there. And then what they have happen, again, like I said, they think about this like a parallelogram. So they imagine that this vector Q is also right here. Okay, let me change that line style for that one. Let's make it dotted. So they imagine that that vector Q is also right here. And they imagine that that vector V, clone it. Oops, not get rid of it, clone it, is also right up there. Okay, let's make it dotted as well. And when they complete this, the diagonal that cuts across it, come here, you. Come here, red vector. That diagonal that cuts across it is the addition of those 2 vectors. So it's like they complete the parallelogram. Okay? So be on the lookout in this second problem and third problem, which I will get to about subtracting. Look for a picture that looks like this or like this guy. Okay? Make sure that you are looking at these pictures very, very carefully, because the vectors, they have little arrows on them, and so you might see a vector that goes up here, and both arrows are pointing to this little corner right there, and that would be incorrect. So really make sure that you look at those arrows very, very carefully. They have to look like one of these 2 pictures. All right? Look at the arrows of the vectors and see where they're pointing. All right? So there we go. That's how we add 2 vectors. That's really what's going on behind the scenes. Okay? Now, subtracting. Subtracting, if you really remember, subtraction doesn't really exist. Okay? Subtraction is really adding the opposite. So this A minus vector B over here is really A plus a negative vector B, okay, or plus the opposite of vector B. All right? That's really what this A minus B is. So if we think about this, again, in those same terms that we had a second ago, this is my vector B, right? So if vector B picks up here, I really need the opposite of vector B. Okay? So what is the opposite of vector B? Clone. And I need to turn this 360 degrees and flip this up and down. There we go. There is the opposite of vector B. Okay, so that's B. And then right there, that's the opposite of B. So they're looking for this line connecting from here to there. Okay, that right there would be the A minus B. Okay? Just like what we did before. We just had to generate the opposite vector first. And then now you do the same thing that we just talked about. We can pick up at the end of the vector with the other that's being added on. So see, we did our vector A, and then we picked up with the opposite vector. Or, again, we can clone this. Clone. We'll move this down. We could have them all start from the beginning. So they both share the initial point, and again, that's the original vector B. The opposite vector looks like this. Okay. That's the opposite vector. And now all we have to do is draw in the rest of that parallelogram. Because remember, I said that the parallelogram really does exist. They think that this guy is there. Okay. And we'll make it dotted. And they think that this guy exists over on the other side as well, too. And again, we'll make this guy dotted. So there's the complete parallelogram for that. And there's that A minus B vector again that connects the diagonal of it. So again, you're going to have 4 pictures. Watch the arrows. Make sure that you're looking at the opposite vector. Okay? And yeah, you just pick the picture that matches the correct information. I'll give you a hint. They love the parallelogram idea for both of these. They love that parallelogram idea. Okay? So that's the first part. And now let's actually start talking about a vector. So here I have a vector. So the first thing they want you to do, some of these things that they want you to do is you need to make sure that you can name the position of this vector. Give me that sort of, in quotations, X and Y. Okay? So we want to know, this is where my vector ends. Okay? This is where my vector ends. That point is going to be used so that we can name this vector. And let's call this vector V for vector. Okay? So this guy up here is vector V. So we want to name this guy. All right. Well, what's this final point? That point that is right there is 1, 2, 3, 4, 5, 6, 7, comma 1, 2, 3, 4, 5. That's where the terminal point is. And that information right there makes your vector. Like I said, it's going to act just like the point, okay? But it's vector notation that we're using. So that's the position vector for this guy, okay? If we want to talk about its magnitude, so if we want to find the magnitude of this, all we're going to do, oops, didn't mean to do that, meant to grab this, is we're going to run, this is my A, this is my B, that little Pythagorean theorem type distance formula, okay? So the magnitude of V is equal to the square root of A squared plus B squared. So that will give you 7 squared plus 5 squared. So that's 49 plus 25. So 49 plus 25, 49 plus 25, 74. And the question is, does that reduce? Because they do want you to reduce your radicals. They do not want decimal answers, okay? So 40 or 74, can it be divided by 4? Nope. 74 divided by 9? No. 74 divided by 16? No. I don't have to worry about the 25. What about 36? Nope. 74 divided by 49? I don't think that's going to work. Nope. So that is the magnitude of our vector. And if you want to find the angle of our vector, okay, we can do tangent theta equal to our A over the B. Okay, I don't know why I wrote it down there. Let's just put it over here. So tangent theta is equal to, sorry, it's not A over B, it's B over A. Silly me. Is equal to 5 over 7. How do I get theta by itself? Inverse trig. Tan negative 1. Tan negative 1. So we just go to our calculator. Second tangent, alpha y equals 5 over 7. And there's our angle. 35 point, let's just say round to the nearest tenth, 35.5 degrees. There you go. Okay, so that's some basic information. If you got a standard position of a vector, and you can find the standard position of a vector, it's not that hard. Just look at the terminal point, and that really is the standard position. You can find the magnitude, you can find the angle, you know, all pretty easy stuff. Okay? Now, they want you to be able to add, subtract, find the opposite vector. Okay? So this is where my notes are going to come in handy, where we're looking at the operations between two vectors, because what we can do is we can find the standard position for each one of these vectors and do some adding and subtracting and some opposites, because all you guys are doing you're not doing this stuff, okay? This was the basic idea behind adding and subtracting vectors, okay? That's what this stuff is. Now we actually want to work with numbers. So it's going to be very, very simple, I promise you. So we can find this terminal point here. We can actually name our vector B for that terminal point, which is 1, 2, 3, 4, 5, comma, 1, 2, 3, 4, 5, 6. So there's vector B. Vector A is 1, 2, 3, 4, negative 4. 1, 2. So all that happens if you're looking at the notes, it's like the x's are going to add and subtract each other, and the y's are going to add and subtract each other when it comes to these. Okay? So if we're looking at this up here, if I'm taking the a plus b, I'm going to take negative 4, comma 2 plus 5, comma 6. Yep. 5, comma 6. And all I'm going to do is put those, like, quote unquote, x values together and y values together. So the addition vector looks like this: negative 4 plus 5, comma 2 plus 6. So when I add the two vectors together, I get 1, comma 8. And if we actually followed those steps that we talked about at the beginning, when I showed you those two, and actually made our vector parallelogram up here, you would see that at 1, 8, that's where these two vectors would actually meet. That would be my addition vector. Pretty cool. Subtraction. Well, remember, subtraction does not really exist. Okay. All subtraction is plus an opposite vector. Okay. Opposite vectors are very, very easy to deal with. All you do, switch the number signs. That's an opposite vector. You're changing the direction. Change the signs. Okay. So an opposite B would be a negative 5, negative 6. Okay? A negative 5, negative 6. That would be the opposite of vector B. In other words, the opposite of a vector changing the signs is like multiplying by a negative 1. So what we're really working with here then is negative 4, comma 2 plus the opposite of B, which is negative 5, comma negative 6. Pretty straightforward, right? Not too hard. And then again, all you're doing is putting the quote-unquote x's together and the quote-unquote y's together. So negative 5, negative 4 is negative 9. And 2 and a negative 6 is a negative 4. And that's where your vector that's the position vector for A minus B. Well, hopefully the opposite of A right here would be really quick and easy. Nothing crazy going on there. So the opposite of A, just flip the signs. 4, negative 2. That would be the opposite vector. All right. Okay. So now we're going to head into what we call a unit. Oh, nope, sorry, not a unit vector yet. Now what they want you to do is they actually want you to find the name of this vector, okay, the position of the vector. Now, please know that, yes, it kind of looks like it's intersecting right here at that end. But because we have a magnitude and an angle this time, we got to do something else to find it, because the name of this vector is not going to be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This vector is not 6, comma 6. Okay. So we got to use the magnitude and the angle to help us out. And in our notes, there are two formulas. One that says A equals magnitude of your vector cosine theta. And another one that says B equals magnitude of your vector sine theta. This is the horizontal component, like the X value, quote unquote. This is the Y value, quote unquote. Okay? So these are what they wanted. This is what they are wanting you to run. Simple plug and chug. A lot of this stuff is like some very simple adding, subtracting, and multiplying, and then a little bit of plug and chug right here. So the magnitude, that's what the 9 is up here. That's your magnitude, if you didn't guess that already. When it kind of looks like the radius of your vector. So this guy right there, that 9, that is your magnitude. And then obviously you should know that this is the angle. Okay? All you're doing is plugging in, kicking out some answers. And they do want exact answers for this. So they're going to give you numbers that will produce exact answers for you. Okay? So A is equal to 9 cosine 45 degrees. The B component, or the quote-unquote Y, will be 9 sine 45 degrees. Okay? And if you go to your charts and use your charts, you find out that cosine 45 is the square root of 2 over 2. Sine 45 is the square root of 2 over 2. And all you have to do is multiply these out. Remember, the 9 is over a 1. And to multiply fractions, all you do is multiply across the top, across the bottom. So in the end, our vector ends up being 9 square roots of 2 over 2, comma, 9 square roots of 2 over 2. And there you go. That's it. So you will need to use that chart that has all those different angles on it for this, depending on the angle that they give you. Okay? All right. So let's talk about unit vectors. Unit vectors are pretty cool. So the I right here represents the horizontal unit component. The J represents the vertical unit component. Okay? So down here, if you've got some sort of standard position vector, over here, we basically just split it up into its horizontal component and its vertical component. Okay? It's just another way to rewrite vectors. That's all it is. So for instance, kind of give you an example, if I had a vector of -2, comma 3, it would look like this as a unit vector. It would look like -2i plus 3j. Okay? So that's what the unit vector would look like. It's just another way to rewrite vectors. And all this means right here, this I, is how far are we moving left or right? And right here, all this means is how far are we moving up and down? That's what the unit vectors are. Again, it's just another way to rewrite it. Okay? All right. So what they're going to do now is exactly what they just did a couple minutes ago. So they're going to give you a vector here in unit vector form, and they want you to do some adding or subtracting. Now, here's what you can do. They are giving it to you in unit vector form, and in your notes, I gave the properties work the same way. It's kind of like adding and subtracting like terms. So we can work with this as unit vectors because, again, in the end, they will want the unit vector answer, just so you know. If you're working with unit vectors, in the end, they generally want unit vectors. So if I'm going to take and add these, I've got 3i plus negative 2i plus 5. Okay? So, like I just said a moment ago, all they're really wanting you to do is put them together as unit vectors. Okay? Put them together as unit vectors, which just means combine like terms. So 3i plus negative 2i is 1i. There's no j's to go along, so that's 5j. And there's an answer. Again, though, just remember, a unit vector is just another way to write a vector. So up here, this, if you want to work with it in that position vector, all this guy really is 3, comma, since there's no j, that's 0. Over here, this is negative 2, comma, 5. And then you can go right back to what we just did a couple minutes ago, right here, where you can add and subtract the quote-unquote x pieces together and the quote-unquote y pieces together. Works the same way. And if you did that, if you put these together in that form, 3, 0, plus negative 2, 5, you end up with this for your answer, 1, comma, 5, which again, in unit vector form, looks just like that. Like I said, it's just another way to write it. Okay? All right. Let's see what else we got here. Dot products. Dot products. Nothing crazy there. So a dot product, it looks like multiplication. So that little dot there, we're not multiplying those it's kind of like multiplication, but it's called a dot product, okay? And so there's a nice little formula for it. It looks like this. So you're going to take the position vector AB and dot product position vector CD, and you're going to end up with a single number answer for this, okay? This is not going to be written as a vector. It's a dot product. And so basically all you're going to do is multiply the quote-unquote x parts, multiply the quote-unquote y parts, and then add it up. That's a dot product. Okay? So in this next one, here they have given you vectors. Sometimes they will give the vectors to you in unit vector format. So they might say 5i plus negative 2j. Okay? And negative 3i plus 3j. So again, if they give it to you as a unit, you can always turn it back into the position. It doesn't really matter. But again, this is the x part, quote unquote. This is the y part, quote unquote. Same thing over there. So dot product says all we're going to do is take the x piece and multiply them together. And add that with the y piece and multiply them together. So what's 5 times negative 3? Negative 15. Plus what's negative 2 times 3? Negative 6. What is negative 15 plus negative 6? Negative 21. And there's the dot product. Okay? They also might ask you to find the angle between them. The angle between them. Okay? Well, that's not too crazy to do. To find the angle between them, if you're looking at the back, it's right down at the bottom. It is a formula, or another way that you can find dot product if you know angle information. On the back at the bottom, if you take the magnitude of your first vector times the magnitude of the second vector, times the cosine of the angle, that will give you the dot product. But in that last question that we're working with, this one, they want the angle between these two. So we can take that formula that I had just a second ago right here, and we can modify it. We can solve for cosine theta, because remember, this is equal to the dot product of V. So if I solve that for cosine theta, this is what the formula looks like. Cosine theta is equal to the dot product divided by the magnitudes multiplied together. So to find the angle between, you're going to end up taking cosine inverse of that fraction. So this will help you find the angle that is between. So we need to get some information before we can find this angle. We need to get 3 pieces of information to be exact. We need to find the dot product between the two. Then we need to find the 2 magnitudes. Okay? So dot product, we already know how to find that. We're going to multiply the quote-unquote x's together with the quote-unquote y's. So our x's are 4 and 1. And we're going to add that with our y values, -1 times 4. So that's 4 plus -4, so that is 0. So there's our dot product. If you find the magnitudes, okay, remember magnitude is the square root of a squared plus b squared. So this right here, let's mark this out. This is the dot product. Fix my V. So the magnitude of U equals square root of 4 times -1, or 4 squared plus -1 squared. So that gives us 16 plus 1, square root of, and then the square root of 17, and that does not break down. Our dot product for V will actually be the same as well. It's not always going to work out like that, just so you know. So the dot product of V, you end up with the same numbers underneath, just 1 squared is first and then 4 squared, which will give you the same answer as the square root of 17. And now all we do is we plug into that formula that we saw up above. So theta is going to be cosine -1 of 0 divided by square root of 17 times the square root of 17. So we go to our calculator and we run that information. Or, you can do some simplifying. Square root of 17 times square root of 17 is just, square root of 17 there. 17. And that gives you 0 over 17. So really all we're doing is we're finding cosine -1, or the inverse cosine of 0. Okay? But again, you could just put that in your calculator the way that you saw it right there in the fraction. We've done that multiple times. So second cosine 0. And it's 90 degrees. That's the angle between. So there is a vocabulary word called orthogonal. And these 2 vectors are orthogonal. Okay? Whenever you have a dot product that equals 0, that means the vectors are orthogonal. Orthogonal means that they are 90 degrees between the 2 vectors. That's what orthogonal means. The vectors are perpendicular, in other words. So you will have 2 questions in your assignment that says, hey, are these orthogonal? All you do is run the dot product and see if it's 0. If it's 0, then the answer is yes. If it's not 0, the answer is no. And that is 11-3. Enjoy.